Okay. Hello. In case somebody didn't notice, I did finally get through. I had a bunch of emails, more so than normal. Of course, in online classes, you get more emails because they can't come to your office. Students cannot come to your office, so obviously you send more emails than you would otherwise do. But I think I got through all the emails. I did notice that some students missed some of the questions because they didn't just scroll through the exam. I don't know what to say about that. I don't know. I can't make you do that, redo that part now. What I would say is I didn't actually take any points off for being a little bit late. But yeah, but giving me answers a day later or something like that because you missed some part, that's hard to deal with. The only thing I would say that I can tell you is that my plan is to grade the mean of the class to a higher grade than I would otherwise do it. So that might take care of some of that. So you might not end up with, anyway, it might not be so bad. If you're not happy with your first exam, again, please try to focus on doing Master in Physics. I did say I was going to send the Master in Physics grade so far. I never did do that. I just remember that. Sorry about that. I will definitely get to it so you can figure out how you're doing on Master in Physics. I will, since you're getting used to it and so on, I will not weigh the first exam as much as, say, the final or even Master in Physics, and I even may weigh it less than the second exam as well. But I still, I have to count those grades. We don't have enough exams to throw away a grade. I do that in my astronomy class because we do more exams. But here, I just couldn't give A, Bs, and Cs. I think I might have mentioned this, but let me say it again. I did discuss the situation with grades with because I'm not going to San Jose State these days, obviously. So I'm not discussing with other professors that much. But basically, my sense from talking to the chair of the department, Monica Kress, is that we still would like to do grades, so we have to still give A, Bs, and Cs. I will try, unless somebody, actually there was a student that didn't turn in, I don't know, is the student here? There's a student that didn't turn in the exam. So of course, if you don't do that, I don't see, okay. If you don't turn in the exam, of course, that's trouble. That could mean not passing, of course. But other than that, I'll try very hard, I'll try, please do a decent job on Master in Physics. I'll try to weigh Master in Physics. That's something you have under control. You can control that just by putting a little bit more time into it. So I'll definitely try not to flunk people, of course. In this situation, it's kind of harsh to flunk somebody. So I'll try very hard not to do that. But if the issue is that it's not about flunking, that you don't want to get a low grade anyway, then let more office hours before the next exam. I did get some students that kept insisting that maybe it was the Master in Physics or something else that was the problem. They weren't doing, they didn't get assigned. No, this is a completely different situation. There's not going to be any better situation than me giving you all the problems in advance. So what I can do for you is to give you the problems in advance a little bit more earlier, to give you more of a chance to do more office hours and go through the problems in office hours. So I can change that part of it. So basically, for the next exam, I will give you more of a chance to, since I don't know, he told me what the problem was going to be, since I don't quite get it. So let me have office hours. I'll give you more chance. Last time, a few people did show up to office hours, but actually only it was only one office hours, really. So let's do more office hours this time. Instead of just 1 office hour, let's do 2, 3 office hours where I just say, okay, today office hours, see who hangs out. And then I just help whoever is there. So that would be right after class. Now, I've mentioned all of that before, but that's really the solution. There's no other solution. I still have to give A, B's, and C's. I can put the mean of the class to a B, which is higher than I would otherwise do. But again, some people did. I'm personally, I'm pretty satisfied with how it went. What happened. I know if you're in the case that you didn't see some of the questions in the exam, of course, that's kind of a bummer. I don't know what to do about that. I'm not sure. So let's try to help you to do better in the next exam. Okay, anyway, I will be a little bit more lenient because it's true that more irregularities are happening online than they do in person. That's true. Just like people not scrolling through the exam. That doesn't, when in person, that doesn't really happen. But I guess I had a couple of students that happened to. Okay, anyway, if you're not happy with your grade, let's start doing well in Master in Physics and let me know before the next exam and let's do a bunch of office hours. And I'll really try hard to help you in the next exam. Now, as far as everybody, I put everybody's grades up. Some people have said, I'm not gonna deduct any points this time around for late because everybody turned it in pretty quickly, pretty soon, you know, after the deadline. So I can't bring myself to take points off. But if the same student does it again, then yeah, I could take points off in that case. As long as it's a different student, then I won't again not take. But if it's the same student doing it twice, then that could be an issue. Let's see, what else? Yeah, I'm pretty much done with grades. Now, if some of you again did send it to my email, so you're actually not able to get the feedback on your exam. So if you want to see how your grade turned out, they're already on Canvas. I just put them before the class. I put them on Canvas. But if you want to see, you would like to know what happened in your case, then yeah, I have the exams in front of me. So just hang out after class. It's not that many students, so we should be able. I can put you on Hangout on the breakout rooms and then just discuss your case individually with you, if you would like to do that. So again, there's not that many students, so that should go fairly fast, depending on how much detail they want to know, but that should go fairly fast. So just if you want to do that, please, absolutely, at the end of class, I will do that with you. I don't have anything else to say about the exams. Again, on my end, I understand there was more spread than normal, but people did do very well. You know, some students, quite a few students did pretty high scores. So the mean was like 21, as I was mentioned last time. So that's good. That's a little better than normal, actually. Maybe I give a little more detail. But there was more spread than normal as well. Okay, anyway, let's move on. We have to. We're running just a little bit late. So I would like to cover chapter 25 as much as possible of this, maybe the whole thing actually today already. I'll give a few practice problems next week already on, I'll do again practice stuff. But right now, today, I have to get through this resistance and PowerPoint because I am running a little late. So my hope is to cover the entire thing today, the entire PowerPoint. It's not a super hard PowerPoint, in my opinion, because some of the material in this PowerPoint is kind of related to how things that we did already. So it's kind of like the capacitor thing, except the rules are somewhat reversed. But we will learn something already today, which is that in general, you don't need to use the equivalent capacitance, equivalent resistance rules to solve circuits. And right away, we're going to get into that because I would like you to realize that you don't need to start thinking like that. There are other ways to do it. It may take a little longer to do it the other way, but it's conceptually it's clearer what you're doing. So in some ways it's worse because it takes a little longer, but in some ways it's better because you don't get confused about what you're doing and how you're supposed to, the process of creating an equivalent circuit and then moving back when you were asking about something about the capacitors. People did lose, I did go through that in class, but people did end up losing points on that. It turns out you don't need to do any of that. You don't need to do the equivalent stuff at all. You can just use rules that allow you to write equations and solve anything you want without doing equivalent capacitances at any time or equivalent resistances. The stuff about equivalence, all of that is in here, so I'll go through it. But very quickly, we'll get to a different way of doing it. They're called Kirchhoff's rules. I don't exactly know what you're doing in the lab, but there was, when we did it in person, there was definitely a lab where you were supposed to check these rules in the laboratory to show that it worked just fine. And these rules allow you to, actually that lab works. Some labs don't work very well when you do them in person. Oh, you did do that already? Oh, okay, great. So yeah, so again, we're gonna do that today, the junction and the loop rule. Okay, so you already have a little bit of training on that. So it sounds like I'm a little bit behind the curve here. I better get to it. So some of it might be reviewed. It might be okay to review it. I don't know how much detail they went into in the lab. How long, was that the last lab, Jason, that you guys did? Even before that, really? Oh, wow. Well, it sounds like they're changing the format then, because that's a little early in the class to start discussing that. But oh, I see, different, right. It's a little bit of a mess, right. Okay, got it. It's okay. I mean, we're gonna go over it again. There used to be some labs that more or less, I don't know if that's what they're doing now, but in lab I remember, I actually avoided teaching lab. I didn't want to try to teach lab in online format because I had no idea how to do that. And so therefore I passed on the trouble to somebody else who has to figure that out. I don't know exactly. So anyway, I bailed out of that one. When we did it in person, the idea was that in the lab, we weren't supposed to teach you so much physics. But now I imagine that they're trying to teach you physics because that's how they're replacing some of the labs. I don't know exactly. But anyway, if it's repeat, then it will find it easier. Of course, the Kirchhoff's rules are going to end up in the exam. So maybe it will be a different point of view on the same thing. So that might actually help out. Okay, anyway, before starting with that, let me tell you that when you start to solve circuits, it's actually useful. Now, if you haven't noticed, we do avoid to do calculus as much as possible. Gauss's law, the whole point of Gauss's law is to avoid doing calculus, really. In general, you would have to do a lot of calculus. There is a little bit of calculus in master in physics. I'm trying to avoid as much of calculus as possible, and I'll certainly try to avoid it in all the exams. So if you get the calculus correct in the master in physics and that helps you to think about things, awesome, that's great. But I'm trying to avoid it. Nevertheless, when you're solving circuits, if the circuits are AC in particular, there is immediately a lot of calculus that you would need to solve those circuits. And let me tell you just the basic idea where the calculus comes in based on this equation here. And again, we're gonna try to avoid it, but later on when we avoid it, we'll avoid it by giving answers, but not because you didn't have to do it, really. To really understand the problem, you would have to solve the calculus. It would be like a differential equation. I just want to point out where the differential equation part of things starts to come in. And already from this equation, you could already see where it would come in. So let me show you, just without solving problems or anything. Suppose all I have is a capacitor, that's it. And I just ask a very simple question. Okay, this is supposed to be as simple as you possibly can. Get a setup where you would already have to worry about calculus. Without actually, we're going to try to avoid it, but I'm telling you that in general, yeah, there would have to be a little bit of calculus to solve some of the circuit problems. If it's an AC circuit, we save that for last, but definitely AC circuits means the current is always changing. That's what AC means, right? So in those situations, you really cannot avoid doing some calculus. But let me tell you why. The first thing that you're going to learn here, of course, is not so complicated, is that there's a definition of current that is microscopic, meaning you're just counting charges going by. That's what current is, right? If there are no, you set up a situation, that's what they're trying to tell you here. You set up a situation in a wire where you see charges going by some location, so there is some boundary, and then you just look at the boundary and say, oh, a charge went by, a charge went by, a charge went by, and charges have very little, charges are electrons, even though here it looks like they're positive charges moving. The reason why they're doing that is because it's the convention to say that the current is the flow of positive charges. That's not really true. Of course, that's not the protons and the ions in general are not the things that are moving. It's the electrons, right? But this is a definition, yet another one. There's tons of definitions in this class. So in this class, we define the current as the flow of positive charges. So that's why that you have to just know that it's not that big a deal in that case. But in any case, they're defining the current to be that way, and then they're showing positive charges moving that way. Well, that's the same thing as negative charges moving the other way, which is what actually happens. But anyway, just for simplicity, always visualize current as the flow of positive charges, even though that's not really what happens, and that you won't get in any trouble for that. So they show here the current and they show charges, and you can think of it as being positive charges. So if you want to know what the current is, and let's not get too much into it other than to see that the units work out here. So you have to let me go through the symbols and work out the units to see that, yeah, that gives you a current. And then if the units are fine, then this equation looks like it should be fine. That's when you do units, you could go wrong with factors of unity, but there are no factors like that here. So just working out the units will be fine in this case. So what they're saying here is that the current has a meaning, a very specific meaning in terms of counting charges that go by some boundary that you choose. So you set up a boundary in a wire, and then you start to count how many charges go by per unit time. So that's the dq dt, and that's the current. So just from that definition, you can tell that, you say for current, you say amps. Well, obviously from this definition, that's just coulombs per second, right? So you do need a dq dt, because again, the current could be a sine wave. And so, that's not, when you have a sine wave, you take a derivative or you take an integral, that's not one number, that's not 5 amps, that's a varying quantity. So you're definitely going to have to start doing calculus when you do that stuff. But in any case, let's just do the units right now, and then we can see how it would work out for this capacitor and see what the formula would tell you, okay? So just the units, how do the units work out? You have little n, so what would be the units of that little n here that they give you? Little n here means the concentration, it says what it means, but what would the units be? So the units would be like number of particles, so number of charges in this case, since that's what they're talking about, charges, per unit volume. So little n, the units of that is simply a number, which is 5. That doesn't have any units. So per unit volume, so that would be like meter cubed, 1/meter cubed, say, since we're doing MKS. So the units of that is just 1/volume. Okay, for Q, the units of that is coulombs. So now when you do NQ, now you multiply by coulombs. So that would be NQ. So I'm going to put the whole thing anyway. I'm just writing the units, so I don't have to keep changing the thing in front. So N is 1/meters, that piece. Q is the coulombs, so that's just coulombs, C for coulombs. VD, that's the drift velocity of the particles. Now, that in general, people think that quantity should be very fast. So because when you turn on a switch, then the light turns on very quickly. It seems like the particle is moving from the switch to the light as soon as you flip it. That's not the case. What travels is the signal. It's kind of like it's kind of a little bit like sound waves. Like the particles don't have to move as fast as the wave itself. So the signal travels very fast, but actually the electrons is even slower. Normal particles move pretty fast in the atmosphere. The electrons, we're going to see later a simplified model why the electrons are not moving fast. Okay, so there is at the very end of this PowerPoint, there is a little model, a little picture model of why this is true. But the electrons don't move very fast at all. They're moving pretty slowly. So this V drift is actually very slow. This velocity speed here. One thing I should warn you about, just very briefly, I don't want to get into this too much, obviously, because it's just to tell you that we're not really going to give real answers to pretty much anything having to do with solids of any kind. So this is called solid state physics. What happens inside metals and inside different conductors and inside things that are not even conductors, semiconductors, and so on. Or what happens in superconducting situations and all of that. All that stuff is really, you can't understand that. You cannot, superconductivity, for instance, is purely quantum physics. There is no analog to superconductivity in classical physics. But you haven't learned quantum physics. So how would I explain that? Well, I can't, so I'm not gonna. So all the models that show up here, they're really thinking models. They're not calculating models. They're just like, oh, it's a little bit like this. It gives you an idea, but you couldn't really calculate anything with it, really. It would be a total waste of time because the physics is not captured in anything you know about. You gotta go to quantum physics, it's all quantum physics. In fact, somebody did a calculation recently. I saw it, I read it somewhere. I didn't check it to make sure that, but all of the stuff in Silicon Valley, all the stuff about conductors and everything else, the entire industry, 98% of it depends totally on quantum physics and is not related to anything you know about. So that's a little frustrating because, quantum physics is hard. So that's a little hard to get to that level. So don't get too upset if I cannot explain something in detail. That's totally understandable. You do not have the physics in hand to be able to discuss that, right? So when it comes to superconductivity, I'm gonna jump right through that. Other places you can try to say something about it, but just an idea only. Okay, anyway, so just so that you don't get the feeling that I didn't make it perfectly clear what this means or that means, you're not gonna make it perfect. So for instance, in the PowerPoint, they don't even try. They say superconductivity and off they go. Okay, so that's just a little unavoidable. Okay, anyway, having said that, we'll do the best we can and we'll give some ideas here and there, just based on what the PowerPoint does. So let's finish the units, which is what we were doing. And so we're doing drift velocity, so it's NQ, and then it says V drift. Well, what is the units of V drift? Well, that's just the speed, so that would be meters per second, right? So meters per second for the V drift term. And then A, let's make sure we understand what A means. A is I choose a surface and I count the charges that go by that surface. A is the cross section of the surface I chose. So in this case, it would be the cross section of this wire. I cut it out and then there's a surface area. And the units of a surface area, that's meters squared, right? Like it's area. So of course the units have to work out, and they do. So a meter squared, and that meter cancels out with that meter cubed, and then you get coulombs per second. Okay, so this is just the number of particles in a unit volume. So literally to get the little n, what you have to do is you take a volume, and then you count 1, 2, 3, 4, 5, and then you divide that by the volume. And then you get the little n. So it's the number of charges per unit volume. Okay, anyway, that's what this formula means. But what it makes clear is that there's a connection between current and the flow of charges, dq, dt. Okay, so here's the point that I was trying to make about this. Why does calculus show up? Immediately it shows up, actually. So suppose I have a capacitor, and the capacitor, we already know what the definition of a capacitor is. The capacitor is the charge divided by the volume, the voltage across the capacitor. Okay, so that's the definition. And what the point is that this was a constant for a given set of plates. Okay, great. So now you have voltage and capacitance. Well, what you would really like to know is you would like to know how long it will take for the capacitor, say, to discharge. But the thing is, as you're discharging, you put a charge here. As you're discharging the capacitor, the voltage across the capacitor goes down. C stays constant, but the voltage keeps changing. So that means the current is going to start dying down. Well, how would you solve something like this? I mean, it seems very simple. There's only one capacitor, right? So what you would solve it is just by showing that the voltage across the whole thing has to stay constant. We'll get more into it. But in any case, when you solve any kind of problem, so you put a battery, let me be a little bit more, this way it doesn't make any sense, the way I drew it. Let me just clarify what I did. I did one thing wrong with this. A wire, when you draw just a wire, that means no resistance. That's what you mean by it. Of course, wires have resistance, but to make that explicit, what you really should do to make it clear, what you're trying to do here is you should put a resistance or a battery if you want, but just let's put a resistor, just to indicate that there's always some resistance. You can't have a wire without resistance. Okay, so now I put a resistor there. And now I want to know what the voltage drop across the resistor is. It's going to turn out to be, we're going to find out in a second, IR. I is the current, R is the resistance of the resistor. And that voltage across the resistor must equal the voltage across the capacitor, because that's the only two elements there are. But the voltage across the capacitor is the voltage is Q over C, right? So the voltage here is Q divided by C. That's the voltage across the capacitor. So they must be equal. The Q over C and the IR must be equal, but you still seem to be left with, you have Q here, but you have I there. Well, the thing is you can write I in terms of dQ dt. That's the point. As soon as you do that, you end up with a differential equation, because I dQ dt, now you have a change in time, and then you have a Q on the capacitor for the voltage across the capacitor. This is the voltage here, right? So when you write an equation that some of the voltages, as you already did this, so you already, I'm sure you know what I'm talking about. When you're going around any circuit, the voltage drops and the voltage rises. We're going to do that again in a little second, but they must be equal to 0. So that's going to give you a formula for this. But one of the terms will have a dQ dt. So therefore, immediately you end up with calculus as soon as you do that. And it will turn out that when you solve the differential equation, you get an exponential. That's a little later. Let me not get into that right now. Then you have to worry about what does the exponential mean and so on. And that comes later. But I'm just telling you that as soon as you give in this definition, now you had to do calculus because the dQ dt showed up in there. And that gives you calculus. Okay. Anyway, let's move on. But I think it's at the bottom of this PowerPoint. There have the different, let me just 1 second to make sure I'm telling you. No, it's not in this one. It's in the next, sorry, it's in the next one. They have one where you already have, so I'm glad I'm not going over it now because this is a little early. I'm just premature. I'm just letting you know. So that will be in the next PowerPoint, you'll see that happen, that there is a differential equation, and just for a discharging capacitor, already you need a differential equation. And then you get a discharge, you get an exponential, and it decays with a time constant, which is RC. But anyway, that will come later, but it comes from this definition. That's where it pops up already. That's the connection between current and charges. Okay. Now here they're just trying to tell you. I'll follow the PowerPoint. Let's see how I'm doing with time. I'll really try hard to get through this PowerPoint. I don't think I should spend a lot of time on this PowerPoint. I should spend more time on later PowerPoints, which are a little bit more germane to what you're going to do in the exam and so on. Here, I'll just concentrate on the concepts, and that's pretty much it. I'll try to go a little fast. Don't want to spend a lot of time on this. But here they're just telling you that the stuff about the electrons, the positive charge flowing, that's just the convention. Really what's happening is what I said before, that the electrons are actually flowing the other way. And so the current points opposite to the direction of the electrons. That's a convention. Okay, so there's not. That's just you're going to need a sign in there. Okay, how about this? Well, here, what they want to do, the reason why they're doing this, and it's a little, again, this is just purely conceptual at this point. You're not really, there is a little bit of physics here. Current is the flow of charges. This is physics. Now, for this equation, there's not really any physics. What they're trying to do here is they're just trying to come up with a formula, a definition of something where you can identify, since they know, people know that this is all quantum physics, right? So they want to isolate the things that depend on the material and shut that aside so you don't have to keep talking about it, because they know that you can't talk about it because you don't know quantum physics. So they're gonna redefine things for you a little bit in order to come up with a quantity that depends only on the material you have and nothing else. Okay, so here all they did is they divided out the cross section. So they put a current, and then they divide the current by the cross section, and then they call that something else, J. Okay, and then they leave a quantity here, which hopefully we can define in terms of some material property. Okay, great. Now they're defining this thing. This is the thing that's supposed to be defined, that is supposed to be specific to the material you have. So this is all definitions, okay? So don't get too hung up on this. It's not that big a deal. In the end, you're just gonna use an equation and look up a number in a book, because you're not gonna be able to do any physics. You're just gonna be able to look up numbers in books or whatever. So now they're defining a quantity that's supposed to be dependent on the material only, so the material type that you have. And even that turns out not to be true, as you will see in a second. But that's the hope, that's what they're going for. So they take the electric field in the material and they divide it by this current density. And then they get something called the resistivity, which is supposed to apply to material. Okay, great. So now they're giving you resistivities of different materials. And they give you numbers for that. And so notice the units of this thing. Again, the units is everything you need. This thing is ohms, and that's meters. So they're just saying, okay, this resistivity is supposed to be, for each material, you're supposed to just give a number and you're done. Well, that's not true, but that's what the hope is. That's why they did this, to try to come up with something that you don't have to talk about the material, because you can't. So just shove it all in there into some quantity that you can define for a material, and then you don't have to talk about it anymore. Well, what they find here very quickly is that it doesn't work like that at all. This is the best you could do, but they're showing you here, there are many things. I'll just tell you the things that show this is not true. Actually, let me tell you already, when you define the resistivity this way, just to show you that you're missing a lot of physics, we're still gonna just do this, and that's it. I mean, but the situation is much more complicated than what this definition doesn't really succeed in getting you there. Let me tell you why. It depends what you're talking about, what the behavior of this thing is. This resistivity they defined basically is the resistance of the material to the flow of current. That's all it means. Now that in general will depend on the temperature. That's not what you were hoping for. You were hoping to just get a number and that's it. You were hoping to get a constant that is for copper, another constant that is for iron or whatever. And then that's all you need. But that's not really what happens. What happens is you get a number that depends on temperature. That's what they're showing you here. This resistance of the material to the flow of current depends on the temperature of the material. But actually, the dependence on temperature depends on which type of material you have, which, of course, is not what the whole idea is. That's just complexity, which is very interesting, of course, but is not what you're hoping for in a simple class. You know, in a class that is just trying to deal with current and so on. So basically, this is, let me explain that a little bit more, even though, again, I'll explain it just with visualizations, but there is no formula in here that explains that. But let me just tell you why this is, roughly speaking. So if you have a metal, okay, there is a little model of a metal at the bottom of this. I just saw it when I was scrolling just before. It's at the bottom of this PowerPoint. I'll get to it at the end. There's a little model of these metals in which you can think of, if you can think of this whole metal thing like an electron that's free to move around. We already know that. But then the question is, how are the ions behaving in the metal? So the electron is going through the material, and the ions, you can think of it like a pinball machine. The ions are kind of like blocking the flow of the electrons. They're not moving themselves, but they're blocking the electrons. So the electrons are trying to make it through. Anyway, we're going to get to it a little more, but let me give you the basic just setup, which is not really, in the end, very complicated. So the electrons are blocking, the ions are blocking the electrons, and every so often the electrons interact with the ions, and then they bounce back against the flow. So it is like a pinball machine. In a pinball machine, you put it on an incline, and then you put obstacles, and then you let your metal ball go down, and then it hits the obstacles, but eventually it keeps drifting. So that's what the electrons are doing. And then the question is, that's what prevents the electrons from moving freely, because the ions are constantly in the way. But the question is, what happens if you increase the temperature? What would that do to the metal? So what you have to think in that case for a metal is that these blocking things, the ions, when the temperature is higher, they start moving around, and they become better goalies, basically. They do a better job of blocking the flow of the electrons. So since they block the flow even more, then the resistivity of the material tends to increase. It opposes the flow of the electrons better when the temperature goes up. The ions keep doing this, and then they block more electrons. Okay, so that's basically that, more or less, as you can say, is literally hand waving. But you can see more or less that, yeah, when the electrons are increasing their energy, then they're going to block the electrons a little better. They're going to make it harder for the electrons to get through. The resistivity should go up. And yeah, for metals, that is true. For metals, the resistivity does go up. That's what they're telling you here. As the temperature goes up, the resistivity increases. Okay, so now they put a little formula, which again is just a model. It doesn't explain, there's no physics here. I mean, I go like this, that's reasonable, but that's not physics. Quantum physics is physics. This is just the description of what could be going on here. So there's no actual physics. This is just a description of what happens inside a metal, that the resistivity does increase with temperature. Okay, so that's for a metal. But actually, it's more complicated than that. So you can see where I'm headed with this. That is very complicated, but we're not going to deal with any of it because we can't. And the formulas don't really do a good job of describing any of this, really. So this is just an approximation of some kind where they just put a factor in there to sort of like more or less capture the behavior, but without any real explanation of how they got that formula. That's just an approximation. It's not even a formula, really. It's a fit to a behavior. That's what this formula is. It's not really any physics in here. So anyway, but you do, this does show that in general, in metals, the resistivity increases with temperature. That much is definitely true. The resistivity goes up with temperature for metals. Okay, great. Now, how about conductors? Semiconductors, sorry. Notice what they're telling you here. For a semiconductor, which of course, you know, is the semiconductor industry after all. For a semiconductor, well, the opposite is happening. So how do you explain that? We're not gonna, well, they tell you here in words. Let me repeat the words, and that's pretty much it. That's all we're gonna do. So if I were to ask about this in the exam, I don't even know how I would do that. I would have to ask a conceptual question. What happens if you increase the temperature of a semiconductor? Well, actually, for a semiconductor, the resistivity goes down, meaning it becomes a better conductor. It's easier to move electrons across a semiconductor when the temperature goes up. So that's the complete opposite to before. So why would that be? Okay, so they're trying to tell you here why that is. Of course, I'm not, by the way, when I keep going like this and I just wave hands and everything like that, I don't mean to suggest that this doesn't matter. Of course it matters. I'm telling you, the entire industry based on how the hell do you understand this? So 98% of it is quantum physics. So it sounds like quantum physics is a very important class. Absolutely, there's no question about it. Quantum physics is a super important class. And it will be more important in the future when they do quantum computing. Then everything will be quantum. At this point, at least, computing is still, digital, binary system or whatever. In the future, when they do quantum computer, then everything will be quantum. Then the first class in an engineering class will have to be quantum. How else are you going to do it? But right now, you guys haven't taken that. So all I can do is give you words. So the words here will go like this, is what they're saying here. The words go like this, that in a semiconductor, what's happening is that when you increase the temperature, what you do is, in a metal, there's always a lot of free electrons. So it's not a question of how many free electrons there are. It's a question of the ions blocking the path of the electrons and making it hard for the electrons to move freely in the metal. For a semiconductor, it does matter how many free electrons there are. And when you increase the temperature, what you're actually doing is releasing more free electrons. You're giving energy to the electrons, and then the electrons can go off on their own instead of being tied to the atom. If they're tied to the atom, then they cannot go anywhere. They're in the atom, they're with the ion, they're not going anywhere. But if you give them enough energy, then they get to be free, and then they can move around freely on their own, then that improves the conductivity, so it decreases the resistivity. Okay, so, very complicated. That's the bottom line. It's complicated. That's it. That's, it's very interesting, very important, but, not easy to discuss in this class. And as if that weren't enough, then there is the superconductivity thing, where basically you just, you can't even give a little picture of that, because that's totally quantum physics. There isn't even a picture in classical, what people call classical physics, of why that is. So for a superconductor, what happens is that the resistivity drops to 0. But normally, this is why this is kind of weird and why it's difficult to understand in a normal way, like in a classical. Because what you would expect, sure, the resistivity could go to 0 for some object, but you would expect that would be at 0 temperature when things are not moving at all. And maybe in that case, they're not really impeding the electrons. So you might expect something that looks like this, that goes to 0 at 0. But that's not it. That's not what superconductivity is. Superconductivity, the conductivity, so the resistivity becomes 0, meaning becomes a superconductor, a very good conductor, at a finite temperature, not at 0. And so for a range of temperatures, basically, it becomes a perfect conductor. There is no energy being dissipated. And, and so obviously that's very nice for all kinds of things. But that's not really something, obviously it doesn't go like this. It's a totally different shape. And that's okay. So they say something here I don't think even worth mentioning, because that's really, this wouldn't be in the exam. Let's put it that way. It's very interesting, super interesting, but not in the exam. Okay. Now, of course, we're going to use Ohm's law constantly in this class. That's this thing here, right? Well, if you think about it, I just finished telling, and then, basically, you want to know what the resistance is. So if you write it this way, the idea was, the reason why we did all of these definitions is to hope for a constant here, and then the rest of it, L over A, that's the property of your wire. So the rho was supposed to be something that depends on just copper or iron or whatever else you have. And then the rest of the information was the properties of the system, the setup. The temperature, the length of the wire, everything else should be in here. And this rho should just be a number. Well, it's not a number, it depends on temperature. So what that tells you is that this is not, when people say that this is, what they're trying to treat this as R is a constant, depending on the wire, because it's just rho times L, the length of the wire, divided by A, the cross section of the wire. Well, we just ended up saying that that's not true. So R is not a constant. It doesn't have to be constant. So if for the experiments you do in the lab, sure, you're not changing the temperature that much most of the time. But if you're putting a light bulb obviously you have to change the temperature. So the resistance of the light bulb keeps changing as the temperature is going up. So that is not correct. So anyway, we're still going to use it, but this is not saying that R is a constant. But we're still going to use it as a constant most of the time. I'll just give you in the problems in the exam, I'll just give you R equals 5 ohms. That's it. That's a constant. So that's not realistic, really. But we're going to do it anyway. Okay. Now, let's not get over that. This is something they should really teach you in lab. I shouldn't go over that stuff. This thing here, well, that's just what I said. If in general you're thinking that if I plot I versus the voltage, then if R is a constant, then I should get a straight line. There are many situations where that's not true at all. So we did used to have a lab. I don't know if they're doing it now. It's not that big a point, so I don't want to get into it too much. But where you have a diode. And a diode is nice because it turns to diode in the lab that you're supposed to do. What it does for you is to change AC current into DC current. And the way it does that is because the diode allows current to go through in one direction, but it has kind of like infinite resistance in the opposite direction. So if the voltage is positive, it lets the current through. If the voltage is negative, it doesn't let the current through. So that's tending to strain out. So if you have a signal like this, which is an AC signal, and so half the time is positive, so the current is positive, sometimes negative the other times. So if it gets rid of all the negatives, well, then you're a little closer already to having a DC current. And then you're not there yet, then you do more diodes, and so on. And do diode circuits of different kinds that tend to make it more DC. But anyway, obviously, as you can see, this curve here, that's not Ohm's law. So once again, Ohm's law is this. That's Ohm's law. Where you have voltage and current, they're plotting it opposite, by the way. That's why the slope is 1 over R. They also actually do that in the labs. When you take them in person, for some reason, people like to plot this I versus voltage instead of voltage. So if you plot voltage versus current, then the slope is just R, which is more natural since it's V equals IR. But they're plotting it the other way. I don't know why they like to do that. They do that in the lab as well, in the written lab. But that's not a big deal. It's just 1 over R. The slope is 1 over R in that case. So anyway, this is Ohm's law, but you can see that if you have diodes, then it looks totally different. Again, diodes is something that's good for the lab, but not to spend time here because I cannot explain a diode anyway. So diode, again, is something that in one direction, the resistance goes to infinity. In the other direction is a very reasonable resistance. So that's not Ohm's law again. Okay. What else do I need to explain? Okay, let me focus on this actually, which is something you definitely need, and that's more practical. And now I'm happy to at least for some of the time here to discuss practical things. Now you probably know this already, but let's make sure you do because definitely this is in the exam. And this is not just talk. This is something you need to remember. So let's now we're starting simple here. We can get more complicated later. But let's just make sure we're on the same page based on what they taught you in lab and compared to what's in here. Okay. So we're going to use that rule. So again, you had the 2 rules. You already mentioned it, the junction rule and the loop rule. Now I'm going to make sure that you understand those things. And I want to get to that next, actually. So I may not be able to get to it today, but let's see, probably not. Well, maybe I could try to do that right away. Actually, after this, let's be practical for the rest of the class. Actually, I don't want to keep talking. Actually, there was the model I was going to discuss about the ions going like this. Okay, I'll go to that model since I already mentioned it, but then after that, I'll try to be practical. If I run out of time, then I'll be practical in the next class. Hopefully I won't run out of time. I can start practical today. Let's see, I have 30 minutes. Yeah, I should be able to do that. Get practical right away today. Okay, so here what they're trying to tell you, so basically what you have to, if you want to know whether you want to use the junction or the loop rule, the first thing you have to decide is, do you have any junctions? So sometimes in circuits, they put like little dots, and that confuses some student into thinking there is a junction there somehow because they put a dot in there. That's the junction. A junction is very simple in the end. It means that there is a fork in the road. That's what junction means. So if you don't see a fork in the road, that's not a junction. Just because they put dots some places sometimes, even in these PowerPoints, they put dots in places. That doesn't really mean anything. I'm not even sure why they put the dots sometimes. To have a junction, you must have, or you could have a junction with many, you don't have to have a junction like this. This is one junction. Of course, you could go this way or you could go, so if you have current going that way, you can go that way then, or you can go that way after the junction. That's true. But then you could have more. You could have this, as many as you want. That's one junction still, right? Now, if you have many, many wires, then you should still be able to write a junction rule for that. So we'll definitely do that. Most of the time, you find you have circuits that have that kind of a junction. So you'll get accustomed to that kind of a junction, but that's not the only possibility. Junction just means there is a current flowing in and current flowing out and multiple wires into that place. Now, the junction rule all arises from the fact that you cannot pile up charges at the junction. So whatever comes in has to leave because you have electrons. Electrons cannot be destroyed. We're not doing anything nuclear physics or anything like that. So the electrons are not being destroyed. So if it's not going to stay at the junction, so if it came into the junction, then it better go somewhere else and leave the junction. Otherwise, you would pile up charges at the junction, which doesn't mean anything because that's a wire. Okay, so when we look for junctions, we'll have to find something like that. Well, there's nothing like that here, right? So it's clear you have to apply the other condition. Now, I can try to confuse you. Probably, let's see, actually, hopefully I can get to that. I'll try to see whether what you were told in the lab was enough for you to write always the right equations or not. So after I say this, I'll try that. In a little bit there, I'll ask you a few questions, see what you say about that. Okay, but anyway, let's get through this. So since there is no junction, we're only going to be able to use the loop rule here. So for the loop rule, what do? Well, you just go around the circuit. You pick one place. It doesn't matter where. And you go in one direction. And again, it doesn't matter which direction. You can do it one way or you can do it the other way. It makes no difference. Here, I know what way I want to go because I see this graph at the bottom. So I know what way I want to go based on the graph that I see. But it really doesn't matter which way you go. Okay, you can go clockwise or counterclockwise, and then you just change the signs. Going clockwise and counterclockwise is like multiplying everything by a minus sign. So it makes no difference. Don't get worried about that. Later on, students try to guess which way they should be going. It doesn't matter. You get an equation for whatever you choose, you always get it right. Okay, in this case, I want to match this. So I'm going to pick the direction of the current. Okay, so I'm going to go in this direction. So then I want to, for each thing that I encounter, I have to add either a potential rise or a potential drop. Okay, so you already did this, but I'm still going to go through it because I know this is going to be in the exam and I need to go through it and then see if you got the right idea as it is. Okay, so so since I'm going in that direction, so I'm going counterclockwise, right? So I'm going around the circuit in the same direction as the current, which happens to be counterclockwise. Then since I start at this vertex, then I encounter the battery. So now I have to say, am I going into higher potential or lower potential? Now this is potential volts, not potential energy. So for potential volts, the plus side is always higher. So I go from low to high. So therefore, I'm increasing voltage, right? So then I put a plus sign because when I encounter the element, I go from less to more. So that's plus is a potential rise. How much? Well, the battery, 12 volts. So I go through the battery and I go plus 12. Well, that's what they did here. From there to there, they cross the battery, that's plus 12. So that's what I just wrote, plus 12. Great. Now I continue. What do I encounter? I encounter the first resistor. So I have to say the voltage across the resistor is, I used Ohm's law, is equal to IR. But I need to know the sign that I put for each resistor. So the rule goes like this. The voltage always goes down in the direction of the current. If you go with decreasing, so how you do that is you do it this way. I mean, it's up there, but you can do it this way. You write the resistor. Am I frozen? No. You write the resistor. You draw the current, I, that you're talking about. So you pick a direction for the current. You might end up being wrong about the direction for the current, but it doesn't matter. I'll tell you more about that later. So right now it's kind of clear what's going to happen. So it's clear that the current is going to the right, but you don't have to get it right. You could, anyway, for whatever current you draw, then if the current is to the right, then you draw the plus on the starting point and the minus on the ending point. So that means you're dropping in voltage with the current. Okay, so there is a potential drop. So you start out high. So notice that here for the battery, we started out low and we went to high. Here, because we're going with the current, we start out high and we end low. So I need to put a minus sign for that. So minus, and then I say IR. Well, that's I. What is R? R is 2. Okay, so now I included the first resistor. Well, there's only one current. You can't change the direction of the current. So the only time you change the current, either the value or the direction, is if you encounter a junction. Junctions are the only thing that can change the current. Other than that, you have to keep the current the same because, again, the electrons are not disappearing. So where are they going to go? If they're here, if the number of electrons is going through this section, it's the same thing as a river, really. What's happening is water is pretty much incompressible. So that's like saying that there is conservation of electrons. So in a river, the water, you cannot squeeze the water. Therefore, whatever water amount is going in one piece of the river is the same amount of water that has to go in another piece of the river. So it's the same thing here. You're not making electrons disappear, so you have to conserve the electron number. So the only way to change the current is to create a junction. Then yeah, some of the current goes this way, some of the current goes that way. Then you change the current. But other than that, I have to keep the same current. Anyway, you probably know all this, but I'm just, since I didn't say it, I'm going to say it. Okay, so plus 12 minus I times 2. And then next, you encounter this next circuit, which is also in the same direction. The current is the same direction. So it's minus I times 4. And if there are any more circuits, no, there are no more circuits. And that, since I'm back to where I started and nothing else happened, the wire by itself cannot change the voltage since it has no resistance. So I times R for the wire is meant to be 0 because R is 0. The resistance of the wire, you're saying that's kind of like your definition of a wire. It's supposed to have very low resistance compared to the resistors. So you don't change it anymore. You come back to the beginning, and now that must equal to 0. Okay? So you solve for this. There's only one variable, I. And then you find out what I is, and I turns out to be whatever they tell you here, 2 amps. So of course, 2 times 2 is 4, 2 times 4 is 8. So 12 equals minus 12. It was 12. Well, yeah, that's right. So 2 amps is the answer. When you solve this equation, you get 2 amps. Okay, you probably know all of that. Okay, great. Let me try to, again, I have a little bit more time. Let me try, actually what I would like to try is to see where you are. So I would like to test you a little bit, but before I do that, let me just very quickly, since I mentioned this already, let me show it, and then I'll try to see where you are with this Kirchhoff's rule. See if I can confuse you a little bit. Maybe I can't, then that's awesome. Then you know what you're doing already. Maybe I can, and then that will help to figure out what to do. Okay, so the thing I said at the beginning about in metals, the resistivity goes up with temperature. The idea that people have when they're talking about that in a classical sense is they're thinking of this kind of setup. The pegs are supposed to be the ions. The ions are much more massive. Since they have more mass, then they have lower accelerations. So since they have small accelerations, you can think of them almost like being stuck in place. But actually, the temperature makes them vibrate, like lattice, like in a solid where things can go like this, but they're not going anywhere. Okay, so that's the picture they have in mind when they think of a metal. The ions are kind of like in a lattice, stuck in place, but they can vibrate. So basically, the more surface area these pegs cover, the more they block the way of the electrons. The electrons are supposed to be like drifting down. Now, what the electrons, the reason why in this point of view, very simplistic point of view, the reason why the V drift would be slow is because this is what is called a random walk, right? So a random walk is kind of like being drunk. If you're drunk after a party, then it takes you forever to get home. So your speed, your overall speed is very slow. You get home in the morning, that took you forever. If you're not drunk, you're moving in a straight line, it's not a random walk, then you go much faster, right? So that is, in essence, in this view, that would be the explanation for the V-drift velocity of the electrons being so slow. They're constantly hitting obstacles. So yeah, more or less, eventually you'll get home, but it will take you forever to do that. So that's why the electrons are taking a long time in this view to advance. Nevertheless, the signal travels very fast, so you can still turn on the light. The electron from the being travel all the way there. Okay, anyway, so I said I would say that, so I'm saying it, but let's move on to the more practical stuff. And I don't have that much time left, but whatever time left I have, so let's do the loop rule and the junction rule. And let me try to confuse you a little bit. See if I can do that. If I cannot, then awesome, that's great. Okay, but if I can, then okay, let me draw a circuit which is as simple as possible. But it has a junction. Okay. Otherwise, without a junction, we just did the case without a junction, so that's kind of too easy at that point. But if I just draw a junction, then what I'm going to do is I'm going to have a battery here, and whatever, 12 volts again, why not? And then I'm going to have a resistor here, and I'm going to just label resistors right there. So I'm going to call this 1, and again, this is practical here. So I've been talking, but now let's make sure you get this, because this is stuff that you definitely need. Okay, so I put another resistor, so I'm going to call that resistor. So this is R1, right? And then I'm going to put R2 here. And then I'm going to have another one. And I want to complicate things a little bit more. So I don't want you to figure out immediately what direction the current has. If I just put one battery, of course, it's going to be pretty easy to figure out the direction of the current to begin with. But I want to get it. I want to just relax you of this innate need to specify the correct direction from the outset, which is what students always like to do. They like try to guess which direction the current is going to go in right at the beginning. But actually, you don't need to guess correct. You just write down the equations for your current. That's I will discuss in a second. But anyway, so I put another current here, another resistor, R3. Then I'm going to put another battery, again, to confuse you a little bit, not to make it so easy. So I don't know, whatever. So I'm going to put it against the first one a little bit, like visually against. So I'm going to put 7 volts here just to make it less obvious. So these two batteries seem to be fighting each other, right? Now I'm going to add more resistors still. I'm going to add a resistor here just for fun. or actually not for fun, to try to confuse you, actually, honestly. Here, okay, like that. Now, you can put any resistance. Let's just do, to make it simple, let's R1 is 1, R2 is 2, R3 is 3, just to, and R4 is 4 ohms. Okay? So of course, and then you have 2 batteries and so on, right? So of course, you would like to know the currents in the circuit. Okay, so let's get this started. And again, I'm going to use the loop rule and the junction rule. So I'm going to get this set up, and I'm going to ask you whether I can solve the system I set up. So obviously, I'm trying to trick you. So if you see something that I'm doing wrong, let me know. Stop me and tell me what's wrong with what I'm saying. Okay. Okay. So R1, I'm going to say that it has current I1. So I have 4 resistors in here. So for each resistor, I'm going to put in a current. So for R1, I'm going to do I1. For R2, I'm going to do I2. For R3, I'm going to I3. And I'm going to pick, let's pick directions just for fun. Again, I'm putting 2 batteries, so it's going to be a little hard for you to know ahead of time which direction is going to go, but well, whatever. I'm going to start saying that direction for that current. I'm just pick out of the blue. No idea if that's correct. For the I2, I'm going to say it's in that direction. For the I3, I'm going to say it's in that direction. And for the I4, I'm going to say it's in that direction out of the blue. And then I'm going to do I4. Okay? So what I just did is I have 4 resistors, and for each resistor, I assigned a current and a direction of the current. Okay, now I'm going to try to solve this system. I'm going to use the loop rule, and I'm going to use the junction rule, or you tell me how to use it. And then I'm going to write down the equations, and we're going to see what we get out of it. Okay? Okay. Let's see if we can solve this system. Again, to be honest with you, I'm doing things on purpose that I know students sometimes do, and then they get in trouble, and then they don't get an answer, and then they get flustered. Okay, so that's what's going on here. Let's see if you figure out what's going on. Okay, so first of all, you tell me, based on the setup that I did, let's start with a junction rule. So I have a junction. Okay, so actually it seems like I have 2 junctions, right? I have this junction here. The junction, again, is a fork in the road. So if there is a dot here, that makes no difference. But here there are 2 forks in the road, this one and this one. Well, in general, let me tell you something that happens, actually. In general, sometimes there are, it's not that, of course, you have 2 junctions, but if you try either junction, you'll find out that it gives you the same condition. So let's just worry about one of them. It could be either one. It doesn't matter which. Let's try that junction there. Let's call that A or whatever. Oh, yeah, when I wrote at the top, it does that. Okay, junction A. Okay, so you tell me, you could go ahead and write it if you want instead of me writing it. If we use this junction, what would be the condition that results from using that junction based on the symbols that I wrote for the circuit? Again, we'll just clear this up. Okay, so Jason says I1 equals I2 plus I3. Everybody agree? Okay, let's write that down. I agree with that too. Based on the directions I wrote, this is correct. Now, I'm going to give you a rule that is a little different and more general than what in this situation, it's kind of easy to tell what's happening. So you have some current going in, and then it splits into 2 currents. So obviously, whatever it comes in has to leave. So this is clear. Now I could put more wires in there. So let's talk about this later, though, because this is not the point for this exercise. Is not to rework this, but I can try to test your knowledge of that too a little bit more than I just did. But in any case, maybe you do know it. That's fine. Let's continue. This is fine. I agree with it. No problem. This is correct. So this would be one condition that you obtain from this, from one junction. Now, if we did the other junction, we would get the exact same thing. Okay, so, okay. Now, let's continue. Now let's do the loop rule. Now for the loop rule, you get to choose loops. Okay, so you say what loop you want. So you could do the loop, you could call this loop 1 here. You could do clockwise or counterclockwise. You know, you could on loop 1, or you could say this is loop 2, or you could do the whole thing. Let me give you another, we're gonna get in trouble here. The way I'm going, we're gonna get in trouble. So hopefully that's my goal here, to clear up that trouble. But let me tell you another issue that sometimes comes up. There are several loops you can choose. So people don't know whether they should include all the loops or one loop, two loops. So here's the rule for that. You include as many loops as you need to make sure that that every element in the circuit appears in at least one of the loops. Okay, once you've included every element in the circuit in one of the loop rule equations, then you're done. You don't have to do the loop all around. That's already been included. So what I'm trying to do is, if I do the loop around 1, and then I do the loop around 2, then I've included everything already. I don't need to do the external loop around everything, which sometimes, like what I mean by that, I don't need to go around the whole thing like this. Okay, because I already included every. That's already been included. That's not independent anymore. Okay, great. So let's do 1 and 2 only. Let's not go around the whole thing. That's, again, been done already. So we're going to do loop 1 and loop 2. Okay, so what is the condition for loop 1? What do you think? You want to write it? I think you could probably write it on chat. It shouldn't be too tough. What equation do you go? You can choose whatever direction you want. You can choose to go, you know, clockwise like that. That's fine. Then the battery should be positive 12, right? If I go clockwise, if I go around this way, then it would be plus 12 for the battery. Okay, how about the other terms? Again, we're doing the loop, the left loop. Then we'll do the right loop. And we'll ignore the overall loop around the whole thing, because that's already been done. Once you include 2 loops, you're done. Oh, yes, sure. Sorry. Do we have time for this? Yeah, let's end with this. I want to get to a point. We just have enough time for me to make my point. There's a point here that I'm driving at. That is very important to keep in mind if you want to always get the answers to things. By the way, maybe, let's see. Okay, let's see what Isaiah says 12, and that would be equal to 0. I'm assuming that's what you mean by that. Of course, you add up everything, it has to be equal to 0. So Isaiah is saying, okay, so we have 12, and then we have minus 1 times I1. And it's minus because I'm going in the direction of the current as chosen by me. I agree with that. And then I'm going through I2. So that's why he has I2. And I'm also going in the direction of the current. Minus 2 I2. Okay, great. So I'm agreeing with everything he's written. Then I'm going against the current in I4 based on what I chose. So it would be plus 4 I4. And that all equals to 0. Okay? Great. Okay, I have 1 minute. Okay, great. Okay, based on what I drew, that is the loop rule, based on what I drew. Okay, I agree with the loop rule. Based on the diagram that I have here up here, that is the loop rule that results from that diagram. I totally agree with Isaiah. There's nothing wrong. Everything cool. But we're going to run into a contradiction here very quickly, and I want to see if somebody can resolve it. So now I'm going to do the second one. And in the second one, I'm going to go counterclockwise just to get a plus again for the battery. So I'm gonna do the same thing as I just did. So when I'm going against the current, I put a plus in the battery, in the resistance. When I go, so I'm going this way now. Instead of clockwise, now I'm going counterclockwise just to get the signs a particular way, but it doesn't matter how you go, it really makes no difference. But that would be based on the counterclockwise direction for loop 2, it would be +7, I'm going over the battery. Now it would be plus, and then it would be I3 times R3. And R3 we said is 3, right? So that's a plus sign. The important thing always is the pluses and the minuses based on the drawing. So it would be a plus because the way I drew the current is when I'm going counterclockwise, I'm going against the flow. So that's why it's a plus. Please make sure you agree on the signs. Okay, then I'm going through now I'm doing the right loop, so I'm going through the resistance. Anyway, we'll do this again. I'm just making sure that we're on the same page about the important things here are the signs for sure, but there's other things that you gotta keep in mind as well. Okay, plus I3 times 3. Then now for the resistor R2, now I'm going with the flow when I go counterclockwise. So I need a minus again. Minus 2 times I2. And then I'm back to the beginning already. I'm not encountering any other resistors. So this is equal to 0. Okay, great. So the signs of everything are correct here. We did all the signs correct. Isaias had the right signs in his formula. I wrote these signs counterclockwise here. Everything is fine. But I'm telling you right now that if you try to solve this, this would be incorrect. You would not be able to solve this. Can anybody tell me why? Even though we followed the rules, we drew the diagram, we did the junction, we did the correct directions for all based on the directions of our currents, we did the right signs. I'll revisit that. Of course, I'm going to revisit that because I know it's going to be in the exam. So if you didn't quite get it this time around, please don't worry about it. We're going to come back to this. But I'm just letting you know that even though we did everything correctly, we're still not going to get the answer. Why not? Here, look what happened here. And this is important to keep in mind, okay? And this will be the last thing I say. Look what happened here. We wrote down 3 equations, but actually our diagram has 4 unknowns, not 3 unknowns. It has 4 unknowns. The unknowns are I1, I2, I3, I4. So how on earth are you going to get an answer for 4 unknowns if you only have 3 equations? That's like trying to get an answer when you have, suppose I say I2, so I say 3I2 equals I3. Solve for that. What the hell does that mean? I have 2 unknowns, 1 equation. I cannot solve for that. So if you want to solve for something, you always have to have the same number of unknowns as equations. So why don't we? What's wrong with my drawing? There was something wrong with my drawing. What is it? Could you do the second junction? No, that's not going to help you. That would be a nice thought, but that's not going to help you. Let me tell you, since I run out of time, I cannot draw this out even more. So let me tell you what happened that's wrong. Okay. It's something very clear that happened. It's in my drawing already. As soon as I set the drawing down, I did something wrong, which is this. It's very important. That's one thing, but that doesn't decrease. So the direction for I4 is wrong, but it's more than that. You cannot keep 2 different currents unless you have a junction. Okay. So this is very important. Please keep this in mind. Otherwise, then you get in trouble. Other than this, it's hard to get in trouble with this problem, except for what I'm saying right now. You see where I have I4? I can go from resistor 4 all the way to resistor 1 without encountering any junction. There is no junction in between R1 and R4. I can go from one to the other. There is no junction. Therefore, I cannot change the current. It has to be the same current in the same direction. So I'm not allowed to say I4 in that direction. No, that's totally wrong. What I have to do is replace that I4. Wherever it says I4 in my equations, I have to change that to the same as above. So what would that be? So it would be resistor 4, that's no problem. But the current would be I1 and in that direction. Why? Because it's the same current as the one through the other resistor, R1. Okay, there's no junction in between. So it's not true that we have 4 unknowns. We have only 3 unknowns, R1, R2, R3. That's it. Is that clear what I mean by that? I want to let it go here. That's the place. But that has to be very clear. You see, I1, I can go from what? I go from R4, then I go all the way to I1. I didn't find any junction. I get to keep the same current always. If I can go from one place to another without encountering a junction, I keep the same current. It doesn't matter if there's a battery, a capacitor, a resistor, an inductor, whatever. If there is no junction, I keep the current. Okay? All right, so that's, if you do that, if you set up the thing that way, can't go wrong. You can draw directions of the current anywhere you want, as long as you're being consistent. So if I1 is one way in one resistor, then I1 is that same way in the other resistor. Okay, so I couldn't change the direction of I1. That would be a different current again. Okay, so I1 has to be to the left in R4. Okay, then we can rewrite the equation. Anyway, I'm done. I run out of time. I did say if somebody wanted to stay behind to discuss anything, because some people didn't actually upload to Canvas, so you didn't get any feedback on your exam. So if you're in that group and you want to discuss a little bit with me what happened, actually, just for the people who did that, please don't do that again. Again, it's just